Okay, video number 3. So everything we've been doing so far in these lessons today has been about differentiating, so finding rates. Now we're going to go the opposite way. We're going to integrate, so given rates. So I've got a water tank, and when the draining valve is opened, the tank decreases at a variable rate given by this. T is the time in seconds. I was opening the valve. When the water stops flowing, the valve shuts off. So when V to T is 0, the valve shuts off. When does the water stop flowing? Okay. So V to T is this. Whoops. I want that to equal 0. So we got V to T 1500. So T is dunk 50 seconds. Give a common sense reason because it's flowing out. Therefore, the volume is going down. That's not a smiley face, that's a downward arrow. Integrate to find the volume of the water in the tank and sketch the graph as well, blah, 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 blah. So, there's another piece of information in the question that you should try and find before I tell you what it is, please. So, feel free to pause your video now. So, the volume equals the integral of V to T. And how do we find C? That's correct. Initially, it contains 40,000 litres. So T equals 0, V equals 40,000. So therefore, C equals 40,000. God, they're going to make me sketch this. So volume is 40 minus 1500 T plus 15 T squared. So let's just draw it the axis of symmetry way. So axis of symmetry is 40,000 divisible by 15. No, it's not. Negative B on 2A. So that's 50. And then when T is 50, volume equals, no point trying to show off. I'm definitely doing this in my head right now. Ignore the tapping sounds. Yes, and well, 2,500. Perfect. Okay. Sketch. So we got the y-intercept is 40,000. This happens at time 50. So that's 40,000. 2,500. Okay, and in fact, the graph should stop there. This bit shouldn't really exist because in reality, what's happening is it's doing this, and then after that, it's actually going flat line there because they turned the tap off, right? But let's just do the right thing and draw the parabola. Okay. How much water flowed out of the tank and how much remains? So, oh well, we've already got that bit. That's how much remains. And so out is 40,000 minus 2,500, which is a number on your calculator, 37,500. Not actually on my calculator. Thank you very much. I was thinking about who to yell at then, but I thought, no, I'll just be nice to everyone today. No mean comments today. Frog numbers were increasing in some district. I wonder where they get the name Ranavilla. Anyway. During drought, the rate of increase fell and actually became negative. So that decreases for a few years. the rate of population has been graphed to the right. So that's the P to T, that's the rate of change. When was it neither increasing or decreasing? Well, that's here and here. Right, so that's the P to T is 0, 4 and 12. Decreasing is between 4 and 12. That's when the derivative is negative. Increasing is from 0 up to 4 and between 12 and 16. Decreasing most rapidly is at 8, the bottom. When was it at a maximum? So I'll give you a minute to think about this. So when was it at the maximum? So at time 0, the population had a number, and then now the silly thing to think is that the population is going down there. In fact, what's happening is the population is still going up because the derivative is positive in all of this. It's just slowing the rate at which it's going up. So it's going up until here. And that's actually the answer, t equals 4. Because after that it goes down somewhat before it goes back up again. Okay, now we can't know for sure without doing a little bit more work, but unless this area is smaller, than this area, the answer is at time 4. Okay, the area under the curve is actually the numerical change in the number of frogs. So we go from to P to T is rate, so integrate up, you get P, so that's the number of frogs, and the area is actually the change in number of frogs, it turns out. And because they haven't given us a vertical axis, I don't know whether this number is bigger or smaller than this number, so I'm going to say 4 as my answer. So after that, when was it at a maximum? Oh, sorry, at a minimum. Well, that's time 12. And that's the answer for the global minimum as well, because it's, again, actually we don't know. It depends on this versus this. But because it's gone down, 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 down before it started going up again, so that's when it stopped going down at 12. Draw a possible graph. So here's a possible graph. Actually, I'm just going to squeeze it in over here underneath. So there's an initial population, goes up, starts going down, goes back up again. Goes up, back down, up again. Take 27, up, down, up. Okay, so the stationary points should line up there and there. And because you don't know basically where this is, you can't say much else. During a drought, blah, 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 blah. Okay. So V to T is always positive. I mean, it's 3 times e to the whatever. So it's 3 times positive number, so it's always positive. Explain the physical significance. So it means it's always increasing. So the flow rate is always increasing. Okay, there's always something flowing out. Find the volume as a function of time. So the volume is the integral of 3e to the 0.06t. So that is 3 divided by 0.02 e to the t. So that's 2 100ths. That's 1/50th plus c. So when time equals 0, they don't seem to give me the initial volume. C minus 150 e to the 0.02 t. C is initial volume. Okay, or I could do the other thing called B subscript 0, might be a nice thing to do. how much water will flow from the well during the first 100 days? So there's two ways that you could do this. You could just go take time 100, at the volume. Therefore, change is V0 minus V0 minus, because V0 is initial, then this is after whatever, and so we get 150 e to the minus 2 as the answer. That's the easiest way to do it. In fact, I won't go into the other way. So as v goes to infinity, what happens? Basically what happens is we approach, so as t goes to infinity, v goes to the initial volume minus 150 times e to the negative infinity is 0. Oh, v0 is not the initial volume, I'm sorry. Sorry. Because here's where I was getting confused. I'm just going to call it C and just leave it as C. So I was getting confused. Well, the thing that I did wrong was when I sub in t equals 0, this doesn't go to 0, does it? It goes to 1. So V0 is actually like the initial population less 150 or something. So just that. So I get C minus 150 times e to the 0 plus C. And so that gives me 150. So I might as well go into the other method now. I was wondering why this didn't work, but anyway. So that's the change. Now the other way to do that is to go the volume between 0 and 100. Okay, so that's the change in volume over the time. 3 e to the minus 0.02 t to t equals. And then if you do the integral, blah, 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 you'll sub in 100, you'll sub in 0, which is what I did here. I sub in 0, I sub in 100. Okay. Describe what happens. You approach C. So it does something like this. Okay. So this leads into what I was talking about before. So there's two ways to do this, right? You can just find x. And then you go t equals 3, t equals 0, work them both out. And what you're doing here is you're subbing in 3, so you get 9 times 3 minus 3 squared. Oops. And then you're subbing in 0, 9 minus 0. So alternately, instead of doing all that stuff, you could just go, well, the change, the distance, is just from 0 to 3 of the integral. Oops. And you get exactly the same thing as this. You can do exactly the same thing for the part B and just go 0 to 5 of the integral. And that's just a nice little, not a trick, but a way to do some questions a little bit shorter. Okay, I think I'll stop there because this video is already getting too long. There's some questions. See you later.